So is it 10 past? Yeah, it's 10 past. So, okay. Hello, everybody, and welcome to the, I think, is it 7th PyData meetup of, yes, of 2021. So for the ones that are not so familiar with PyData, we're thinking to show some slides so that you get familiar. And hopefully, if you get familiar, you come to the following meetups as well. So PyData is an international, let's say, educational program that provides a forum for the international community of users and developers of data analysis tools. And it focuses on mainly sharing ideas and learning from each other. It's a global network. It has a lot of chapters in a lot of cities around the world. And the network promotes discussion of best practices, new approaches, emerging technologies for a variety of fields ranging from data management to data visualization. It aims to be an accessible and community-driven conference with talks of any level of expertise, let's say, so from novice to advanced. It's organized by a US non-profit organization. It's called NumFocus. That it continuously sponsors a lot of open source tools. You can see the tools here. I'm sure if you are a data scientist or a software engineer, you most probably have used at least one of them. For example, NumPy and Pandas and scikit-learn for machine learning are all projects sponsored by NumFocus. So in Cyprus, we are the only chapter that exists in Cyprus. So we're the Cyprus chapter, and it's organized by volunteers. So I and Nick are both volunteers at the chapter. We organize monthly meetups, and we are a community of almost 700 members. At the moment, so we are one of the biggest communities that is related to data science. And we hope to become more members and also attract more people to the talks. There are some upcoming events from the global PyData network. Each year, usually there is a conference organized by some of the chapters, but due to COVID restrictions since last year, the conferences kind of unified into one, and they are offering this global conference. It's going to take place at the end of October, and so the program is not out yet, I think, but there are going to be very, very interesting talks on data science and software engineering and so on. And with that, you're always welcome to say hi. You can find us at Twitter here or at our Meetup website here. And currently, I and Nick are the co-organizers. You can find us at our Twitter handles there. If you have any ideas for talks, please come and say hi, and you can present at one of the future meetups. And with that, let's go to Kostas.
Hello, and thank you very much for the invitation to give a talk. Here I'm going to present. Let's see if it works. It did. Just a moment ago. Can everybody see my PDF screen? Like the first slide? Awesome. Okay. So I'm Kostas. I'm a data scientist at Nodes and Links. And the topic of the talk is applying network science along with other mathematical tools. But network science is one of the major fields that we apply. So let me say a bit about the company. We are a VC-backed UK-based company, and the tech hub is in Cyprus. And the idea, what we do is we provide business intelligence solutions to customers that manage the so-called mega projects, so large complex projects. I'm going to give examples shortly. So one second, I'm having some trouble moving through the slides. Okay, it seems to work. So I'm going to give a brief introduction into these complex projects and then move on to what is a project schedule, the type of data that we're dealing with, and the type of tools, as I mentioned, network science mainly, and then give us examples, certain applications. The idea is I wanted to keep the talk not too technical, but rather give more of an overview of this type of data science and this type of data. So the modern economy relies quite a bit on very large projects. So some examples from the UK, France, and Singapore are shown here. The high-speed 2, the rail, running, I think, from the north to the south of the UK, Grand Paris Express, the A14 motorway in the UK, Swansea and Heathrow airports, Thames Tideway is another very big project in London. So infrastructure projects definitely concern a big part of the of economic activity nowadays, and they're very hard to manage because they are quite long term. Some of these projects might take 10 years, might span 20 years. People come and go throughout that span, and the amount of information or the amount of organization, like coordination that needs to happen between several different contractors is enormous. There are many challenges. Think even just Googling any kind of project management string will probably give rise to certain news about projects failing or not finishing on time, not finishing on budget. One sec, I'm going to turn the light of my room here on because it's became increasingly harder for me to read my notes. So as I say, the three main items, the three main aspects of a project that managers are focusing on. One is finishing on schedule. The other is finishing on budget. The third thing is quality. And there is a long history of, as I say, either failure or things just not finishing on time or at the expected quality. There are differences between different sectors of the economy, and also certain differences geographically around the world. But as you can see from this project controls fact sheet, there is a large percentage of unsuccessful projects, at least in one of the respects that I mentioned before. Now, the idea of project controls is this concept is very central to what we're doing at Nodes and Links, because when you have a mega project to deal with, there is a lot of decision making that goes on, and nowadays there's a lot of data. So the collection of that data, the management, the analysis, and the decision making that is led to is in general called project controls in the project management field in the industry. And the main things that the project manager would be looking to being able to do through project controls is manage the project effectively, inform decision-making, track progress, and be able to coordinate effectively. Nodes and Links provide solutions to facilitate and improve this procedure. So far, the industry standard depends, it still depends, I guess, on technologies that were developed back in the 50s and 60s, mainly by the US military. The critical path method is probably the most famous tool of these. And PERT, program evaluation review technique, is essentially a a stochastic variant of this. So in this model, there is randomness introduced. The same technologies, just with increasingly newer software, has appeared in many types, many products. The most famous of which are P6 by Oracle, Primavera P6, and Microsoft Project. So most of the customers would be using one of these two pieces of software to, first of all, collect the data, which is a large process in itself, and then to a secondary degree perform some analysis on them, some computations, in order to provide some estimates, make the decisions. So far, this is the state of the art in the industry. Now, the idea behind nodes and links is to try and bring this field of project controls to the digital age. So essentially, we're providing a cloud-based platform that aims at improving project performance, aims at reducing the risk for the planners and the people that are managing the project. It's a modern platform. There are many different tools and screens in it. Here you're seeing actually an image of the software as it used to be a while ago. There are various graphs. There are more advanced types of visualizations based on network science. There are different types of analysis like critical path and project progress, which are traditional, but are also schedule checking or identifying the most critical paths to any selected activity. For instance, important milestones where quite often the profit or the revenue of these projects depends on. So essentially, the customer would basically be looking to get certain milestones satisfied before proceeding to next payments. So there is a range of different screens and different types of analysis in the product. Moving on to the type of data and explaining a bit about what a project schedule consists of. It is organized in terms of work breakdown structures. This is the most fundamental unit of organization. And beyond that, there is further organization into what are called terminal elements and mainly activities. So activities are essentially the pieces of work that need to be implemented in order to progress with a project and produce a certain deliverable. As an example, here I have the application of oil paint when painting the canvas. There are 6 different types. The main ones are what are the so-called tasks or resource-dependent tasks. But also I mentioned milestones. So milestones do not really have a duration per se. They're more there to satisfy certain progress. And the other 2 types are less common, first of all, and also a bit different in the nature. The main focus is task-dependent, resource-dependent activities in terms of the items that need to be delivered and make the project move on. Now, the idea of why introduce network science into this type of data is essentially due to dependencies. All these activities in a project follow certain logic. There are constraints. There are preceding tasks that need to occur before another task can start, for instance. So completion and initiation of different activities is dependent on these logical dependencies that are set by the planners at the beginning of the project. And here we have 4 different types. So the most common one, finish start, means that a prerequisite task needs to have finished before a succeeding task can start. But there are other types, a bit less common sometimes, but they will actually used in practice. And then another important element of a schedule are resources, which are either people, labor, or it could be materials, or it could be equipment or plant. And a data set of a project schedule consists of several tables that essentially provide information about all these items that I mentioned. There are actually around 20 tables. They're more concepts than I would like to go into in this talk, but I'm just giving some of the fundamental elements. These tables are usually CSV format, and they provide all the information, all the properties, all the attributes of each of these elements. So activities and their attributes, then dependencies will also have attributes, work rate breakdown structures, same thing for resources. And there are always, in a schedule, apart from the relationships between the different elements, there's also the element of a hierarchy. So for example, WBSs are also organized between them in a similar fashion to a folder hierarchy in our computers. So a tree, essentially, in network terminology, it's a tree. And the root WBS, the primary one, is always the entire project. And beyond that, managers are separating into big chunks of work. So electrical, for example, would be different to design, would be different to piping. And this is how the whole structure of WBS is generated. And there's a similar structure for resources. And also, as a user, as a planner, the standard software that I mentioned earlier, which are used to collect this type of data, also allow for user-specified fields. One example is called activity codes. So there are many organizational structures essentially behind these data sets. Duncan Watts is a famous network scientist and has worked in several interdisciplinary pieces of works. And I just wanted to quote him here. Because I think this particular statement of his about the advent of the internet, modern technologies, and also how it will affect the economy or society at large is spot on. I think nowadays there are many different fields rising, and being able to combine them, being able to combine academia and industry and further research is a unique opportunity, at least in the sense of the amount of data that is being collected nowadays. And nodes and links, I think, is an example of such a modern company trying to leverage essentially everything that is going on and bring revolutionizing solutions to a field that has existed for a while, like project management. Let's move on to certain examples now. I'll start with some concepts in order to show you how network science can be used to represent concepts about a schedule, and yeah, I guess give an idea about the connection and how these such models can represent the type of data that I was just talking about. So the most fundamental concept is that of an activity network. Essentially, the schedule that I mentioned, the collection of activities connected to each other by directional connections, the so-called dependencies, the logical dependencies, is directed network, unipartite in the sense there is only one type of nodes, and also unweighted in the sense that these connections, the links, are are essentially the same, uniform across the entire network, the entire project. In addition, there are no cycles, which would constitute a logical error in the sense if task B depends on task A, which also depends on task B, that would be, let's say, a 2-cycle. It is a logical inconsistency. So if the schedule has been prepared in a meticulous way, The resulting network that represents this schedule, that represents this logical dependence between activities, should be a DAG, directed acyclic graph. And there are specific tools and theory within network science developed for this type of graphs. So as I say, this is the most fundamental representation of a schedule, the activity network. And note also that it is characterized by a hierarchical structure. So no matter what layout we use to visualize this type of data, this is a sort of random layout. And earlier in the laptop screen where the product IDs were shown, there was a polar layout. But these types of networks can always be laid out in a hierarchical manner. This is a real world example. So ingesting the data set from a project which consisted of about 550 activities and almost double the logical dependencies. This is a network visualization of it. You can see that there are 3 separate components on it, and one of these components, the nodes are highlighted in red. This would be the nodes of the critical path. So this notion essentially that what a planner and a manager cares about is for the project to be delivered on time. And the horizontal, let's say the imaginary horizontal axis here, moving from left to right, is somewhat representative of an actual timeline. So at this point, we have a project deadline, and a project ideally, we would not like it to be delayed. Now, if certain tasks, certain activities get delayed for some reason, then we can quantify the amount of project delay that they will cause, and then be able to identify the most critical activities within a project. So in the sense of if something goes wrong with these activities, then there's a higher chance that the entire project will be delayed. Now, moving on to the WBS and the folder hierarchy that I mentioned earlier, and I only saw the WBS here, but exactly the similar property holds for the resources in a project. We have another type of graph, similar characteristics to the previous one, in the sense that it's unipartite, directed, and weighted. However, this is a tree structure. So this root WBS at the top signifies the entire project usually, and then beyond that there is branching. And this sort of branching essentially represents the organization chosen by the people that are running the project. And to make things clear, this network is essentially a different network to the activity network. Both exist. So we have the activity network where activities are linked to each other. All these activities are actually classified under a certain WBS because WBS is a more fundamental organizational structure. And each WBS has its own WBS hierarchy. And a similar thing, as I say, holds for resources because activities are also assigned various resources. And usually at least one of a labor resource, at least one of some material resource. And with labor resources, there are many roles as well. So it is quite common that a single activity would have even many labor resources assigned to it. But then the resources themselves are again organized in some other structure, which is also a tree structure. A different example is the activity resource bipartite network. So essentially, perhaps one would like to look at certain critical activities that might delay the project and how many resources are assigned to them, how many different subcontractors are assigned to them, how many, what type of equipment needs to be on site or what type of material. And This can also be represented within a network structure. It is a bipartite graph now, so there are two types of nodes. In the visualization, blue and red signifies the different types. But this one is undirected. There is no directionality, and also it is not weighted. In this particular example, also the size of the blue nodes that are, sorry, of the red nodes that are resources also denotes how many tasks, how many activities are assigned to them, which might be interesting from different perspectives.
Can I ask you a question on this slide, please?
Definitely, of course.
I'm not seeing the relational interdependence between activities here. I've seen this before.
That is true. That is true. Exactly. So because this is a different network, in order to be able to visualize all these interdependencies, we would have to essentially connect this structure to the activity network that I mentioned before in a multi-layer network kind of fashion. So this specific network is a different representation and focuses specifically only on connections between resources and activities. So resource assignment, essentially.
So idea is to get a certain type of insight from such a representation.
Exactly. I think in order to, if the aim, and perhaps a more longer aim, is to represent the entire schedule in as an exact, precise, and as comprehensive as possible view using networks, then we would connect these different graphs and create a very large multi-layer structure. So you would have at each layer would be a network, and then even these networks would be connected with each other. But for now and for starters, even these specific different networks that focus on one particular aspect of a project schedule, like this one, resource assignment, can be actually useful to the people that are working on it, because the people, so our customers, are interested usually to solve the problem in practice. The value offered by this is mainly the informed decision making that they can make, essentially. So even focusing on specific aspects can be very useful in practice. That is the idea.
Thanks, Kostas.
You're welcome. And for instance, here I have yet another type of network. This one is actually derived using the resource assignment bipartite network that I just showed. But it is a resource interaction network. So it's resource. Again, it is unipartite. The only type of nodes here are resources. Also undirected, but it is weighted. And the way it is derived is by checking which resources are connected via their assignment to certain activity. So if two resources are both working on a single activity, we would create a connection between the two nodes. And these connections would be weighted in the sense that if we look at the same pair of resources and they're also working at activity B, so essentially they're working at both activity A and activity B, then we would make the weight of that connection 2 instead of 1. So it is weighted, and the weight represents how many activities resources are commonly working at. And again, this is a different type of network, so it highlights different aspects of the schedule, and in its own right, it can be used to extract some useful information. It will just be different questions that would be asked. So for the activities network that I mentioned at the beginning, the resource assignment network that I mentioned in the previous slide, the bipartite one, and the resource interaction network that I mentioned here, a planner would ask different questions to answer by its structure. Here, for example, it might be of interest to see if we have observed maybe delays in certain activities, or there are certain critical activities that we expect to possibly cause delays, which resources are working on them, if there are issues found, does this relate to communication between certain different contractors? What about material or equipment plans? So there are different types of questions that can be asked from using each different structure. Now, to give you also an idea of the different macroscopic visualization that a product like Aegis can provide in comparison to all the tools, so Gantt charts, and the activity network that would be generated by Primavera P6, the most commonly used software. Well, the juxtaposition is here essentially. Here we have a network visualization. Different components of this network seem to also correlate well with different WBSs. So the names here are essentially WBS names. So visually, at least, I think the difference is noticeable in what network science can provide in terms of viewing project schedules. Now, I thought, as I've kind of introduced nodes and links and then moved on to the type of data, and then moved on to possible mathematical representations that can be used to model this data to extract useful information. And I thought as a next step, it would be interesting to see different practical problems, so different applications of this. And again, an example without going into too much detail about the mathematical approach that can be used or that we are already using. So one problem is delay propagation. Remember these finish-start relationships between activities. So if the predecessor is delayed, the end date is not met, and then the succeeding activities will have to incur delays because of that. So there's this propagation of delays essentially. And one way to look at it in terms of network science is via shortest path detection algorithms essentially. And one can find a specified number of shortest paths, but it's arbitrary actually, K, from a dummy start node placed at the beginning of the project, connected to all root activities. Root activities are those without predecessors, but which have successors. And the same thing at the end, again, a dummy activity connected to all so-called leaves, those activities that do not have successors, only predecessors. And through this augmented network structure, do a lot of basically compute paths, do a lot of path detection using traditional algorithms like Dijkstra, for example, or others if negative weight is to be included. And it's one way of finding critical activities, critical paths through network science. And it is different from what I understand from standard software. Now, a different problem is actually that of delay contagion, which is something that has been hypothesized, perhaps not given as much attention by the original researchers that, for example, formulated critical path method. But the data seems to indicate, to at least provide indications for the existence of a slightly subtler but similar concept in terms of delay. So contagion. So propagation is when the predecessors are pushing succeeding tasks further into the future. However, there's this other notion that there might be some kind of epidemic spreading, let's say, of delay. And this may have different causes. For instance, if there is some subcontractor working on a sequence of tasks or just a set of tasks, a collection of tasks within a project, it could be that there is no delay shifts, no pushing forward, but it could be that there is some inefficiency going on or some other reason why delays occur. So this is a different problem mathematically, because in this case, we would be looking at epidemic spreading, wouldn't be looking at paths and calculating float between the activities. By the way, float, I didn't introduce, but it is a very important concept. It's the amount of time in between connected activities. So once the predecessor finishes, how much time do I have before the successor needs to start? And it is quite important because planners use it to also account for uncertainty and unexpected events. But at the same time, ideally, they would rather optimize the entire process as much as possible for revenue and profit purposes. In any case, delay contagion is different, as I say, problem mathematically, and the type of network science that would be useful here is looking at spreading algorithms, cascading failures, etc. A third problem is that of viewing the schedule microscopically and at a higher level, because these schedules consist of tens of thousands of activities often, and even more dependencies, very big work breakdown, structure hierarchies as well. So there is a large amount of organization, and well, the question is it perhaps possible to understand this whole organization from a different lens, and for instance, applying community detection principles to the networks that we saw, the activity network, for example, and see if some different sort of aggregation arises essentially. And so this is a different, completely different type of problem. It has to do more with human beings being able to manage the project, identify critical aspects, and also track the progress without needing to delve too much into detail. And finally, I have another practical problem, and I thought for this one, as a final step, I might move a bit more into the technical data as well. This also involves some, I would say, statistical mechanics, or again, it's a topic pretty close to network science. Mean field approximations have been used for a while in network science to produce analytical estimates and be able to compare with simulations. But yeah, as I say, I decided this one is a topic that I've worked on personally, and I thought I might provide just a little bit more detail. So rework is another important concept. It is so important because it is one of the primary causes of costs and schedule overruns, and it concerns re-implementation of activities. The reasons, there's a variety of reasons, like omissions or errors or poor communication, failures, changing the specs, problems with documentation, coordination. So there's a variety of reasons. At the same time, in terms of academic research, it is a topic that has not really been addressed that much. And so there are no known tools in order to deal with such a problem, effectively model it and try to extract information from the data. So what we did here is we created a so-called master equation. The idea is, as I mentioned, we have the activity network. So matrix A here now stands for the adjacency matrix of that network. So essentially predecessor-successor connections between activities. And I have a sketch of a very simplified network here. Activity 3 depends on activity 2 and 4 being completed, and they each depend on activity 1 having been completed. 2 and 4 can be worked on in parallel. So for tasks, this type of project would have 6 possible states, which are denoted in equation 2.3. And the first foundational state is nothing has happened, there are no completed activities. Final state is everything has been completed, and we have all these partial states in between. So in this case, there are 6 possible states. As the size of the project, so the number of activities becomes larger, and depending on the link density, so the amount of dependencies, and in some sense, the more the dependencies between activities, the harder it is for a human being to deal with it. So the more complicated it is for a human being. This system of states also grows, and it grows much faster, actually, than it's not equal to the size of the project network. So here we have 4 tasks, but 6 states. Now, looking at transition rates between states, so WKM denotes transition from state K to state M, and introducing some parameters in the model, for instance, a certain completion rate or a certain rework rate, like going back and re-implementing a task, and then doing a little bit of analytics, mainly using the law of total probability, one can arrive at a master equation. And this equation describes the temporal evolution of PK, which is essentially the probability that our project is going to be a state K at time T. Naturally, as time increases, we would like the K state to be the final one. So in this particular instance, S6. And this equation can, of course, be solved numerically, but at the same time, one can look at what happens by setting the derivative equal to 0. So what happens as t tends to infinity in the long term? And obviously, in the long term, it is definite that from a manager's or planner's perspective, PK, where K is the 6th state in the previous example, should tend to 1, ideally, and all other PM should tend to 0. So all partial states, so the incomplete state, should have 0 probability of for the project being occupying them, essentially. So there is, just using this model, this equation, there's a variety of analysis that can be done. And as t tends to infinity, as I say, in that limit, one can also analyze various values for the rework rate. So if we assume a certain completion rate, that could also be drawn from an empirical distribution based on data. So durations of activities, for example, actual durations. One can examine a range of a parameter. In this model, it's called R. I haven't shown it here. And this parameter describes the rework rate. And then one can ask the question, what is the critical value of that parameter of rework that will make my project go from being certain to finish, to being completed, to start being uncertain, to have a higher probability of it remaining in a partially complete state. And based on this idea, essentially, this question, can we examine what happens with different values for the rework rate? What we did was investigate all different topologies of a certain size. So we did it for, I've got results for size 3 and size 4 here. For size 3, and specifically directed acyclic graphs, there are only 4 possible configurations that are shown here, namely the star, the serial connectivity, the inverted star, and the triangle. And I'm showing them here in hierarchical visualization. That's why this does not look as a triangle, the 4th one. But essentially, based on the master equation that I just showed, plus the parameter analysis, the sensitivity analysis that I mentioned, how much rework is allowed before the project starts being less certain to complete, we managed to actually classify all the different networks and say that if you have a star, the score is going to be higher. So we can rank this one. In this sense, the star is more robust to rework in comparison to the other three configurations. Of course, in this very simple setting, it makes sense because here you have only one root activity, and then these two can be performed in parallel. So it makes some sense. Of course, that is always how much sense it makes is always dependent on the parameters that we used. Now, when you move up size, though, for instance, let's go from 3 nodes to 4 nodes. Suddenly we have 24 different configurations. And obviously this number keeps growing. For size 5, there are even more, etc. And starts becoming less trivial as to which topology is more robust, more resistant, more resilient to rework occurring. And note that this is a context agnostic rather than a context specific view of the project, because the question we are asking is not can we predict how much rework we're going to have. It's not which activities are going to be more prone to rework. These are context specific questions, and other type of data than the type that I mentioned, and the type that we have at our possession would be necessary to answer them. But with the data we have, even simply with the connectivity between activities, the logical dependencies, it is possible to ask which structure is more resilient from this perspective. And so again, we have actually ranked and also classified these, because there are 24 different networks, but there are at the same time only, I think, 10 different equivalent classes. So for example, the serial would be equivalent to all these. They are essentially a serial connectivity graph with some extra link. So I'll stop with the technicality here. I just wanted to show that this wealth of data, of project data that we have, is amenable to various sorts of mathematical analysis. And as a company, we're very interested in pushing research further into understanding projects further, into bringing new solutions, in collaborating with universities. And also we're definitely looking for intelligent data scientists that are quite keen to tackle this type of questions. So I think I will stop here. We're probably close to the time limit. And thank everyone very much for listening to me. And it was a pleasure to be invited at PyData Meetup.
Thank you, Kostas. That was super. A lot of information. I will open it up for questions. People are, of course, free to stay or leave and ask questions by unmuting or in the chat. That's up to you. I can see that there is one question already. Feel free to unmute and ask.
Kostas, I've been with doing project management for almost 15 years, with construction guys for almost 10 years. A lot of different kinds of projects, different types of projects. And of late, last 3-4 years, these have become data rich as well. The advantage of data has been, in India at least, towards controllability, not in the sense of project controls, but if you have enough data and you know how to visualize them, you probably can control your projects better, and that's our experience. What I mean, and I've shared my LinkedIn profile. Happy to explore that further. My big question for you today is: most data is lag data. I would like to see AI bring in innovative approaches. One of the classic projects was the Hoover Dam, and it was an 11-year project which Hurry Up Crow, that was the nickname for him. Crow was the project director. He finished it in 8 years. It's just unbelievable for a construction project to be ahead of schedule. And somewhere the birdie in my head says data science complexity could probably, with AI, could probably come about doing such things. So, sorry, big question, open question. Love to hear a response, or maybe
Definitely. No, it's thank you very much for the question, Chandrakar. I first of all, it's something that we hear often, as you said, construction projects being delayed or being going quite high over budget. So it is actually very interesting to hear about this example where it finished ahead of schedule. I agree completely. I think data science can create solutions that will help manage these projects more effectively. And we can already see it, I think, on a variety of levels, variety of aspects. So one, probably the simplest example that I could give is all these data sets that we have. One issue is that they also contain errors sometimes, or there needs to be some kind of processing, pre-processing, sanitization. So when we started creating models and algorithms for nodes and links, this was one of the first things that we had to look just for the sake of our own verification of the algorithms that we're creating, etc. And in the end, this created the product component about schedule checking, essentially. And you see immediately, even such a relatively simple, it's barely data science. It's the beginning, right? It's one of the foundational steps, like clean the data set somehow. But even that had actually a lot of value for our clients, because it's much easier to have something automated, essentially aggregate all types of errors that have been precisely defined and classified, and show them to you on a screen, right there in front of you, rather than have many planners that do know the project, obviously, better than us, but having to actually do a lot of work to look through, compare different things, and use their intuition. It is one of these tasks, essentially, that a machine is essentially better at doing, in order to free the time of the human being to do something more creative and useful. So I think, if even these simple solutions, automating solutions, can help, then actual data science that can perhaps provide more insight about the complexity, provide more insight about how to perhaps plan the whole schedule, for instance, knowing, having some knowledge about what constitutes resilience to rework, things like that. I think in the long term, it is almost certain in my eyes that data science will really help with projects performance, projects efficiency improving.
If everybody is shy of asking questions, I don't mind throwing one more.
Cool.
I can see that Andreas has a question as well.
No, but please go on. No, go on, and then I can go later. No worries.
Yeah, of course.
Yeah, no, I'll wait. No problem.
My audio is going on and off, so I thought you weren't speaking, and then I heard you speak. So feel free to continue your question if you want, or or otherwise, Andrea, you have the floor.
I'll wait for Andrea.
Well, okay, thank you very much. My question may be naive, or I mean, it's just like a question I have. So, for example, in some of our projects that we have here at the Cyprus Institute, one of our issues is that sometimes people tend to drop from the projects. This is very common in PhD like related projects. So for example, joint doctorates and things like that. My question is that, would it be possible to predict behavior, human behavior, given that we have a sufficient data sets from previous sociological studies in order to predict whether or not this project is feasible, or will it need an extension based on certain profiles? So if we have people complete questionnaires before hiring them, giving them an offer, and given that we have big enough data sets, which I guess exist in some capacity, well, if we bypass the ethical issues, because I guess there are many ethical issues on that, will we be able to integrate it in such? Do you believe that it's possible to, in the future, to integrate it and maybe predict, not necessarily reject people, but at least make sure that the risks involved are accounted for in a larger capacity than we're able to do now without these complex models?
I think it's certainly possible to integrate with this sort of data. At the same time, I guess the predictability would really depend on the quality of data that has been gathered already in sociological studies, plus the quality of the conclusions, actually, the quality of the analysis. And that I would probably be a bit more skeptical rather than this sort of data. So this sort of data, I guess, in my eyes, and I've seen, in my experience, many different types. Like I've worked with time series, worked with this sort of thing, worked with positional data from ocean floaters. And over my experience, maybe depending on the field as well, I tend to kind of classify different type of data and their reliability in my mind. And so if we're talking about something, like Argo floaters and oceans, that type of data is more physical type of data. So I have it in my mind as more reliable. I would trust any conclusions more. Then moving on to this kind of data, like project data, where I've seen the various classes of errors that can happen as well with the sanitization, the pre-processing that I was talking about earlier. I have it in my mind as less reliable, but still, knowing the sources of error and having a good sort of picture, good idea, helps a lot. And then moving on to social data or economic data, other types of fields, more social sciences, which I've done to a lesser extent, at least professionally. I have it in my mind as a bit harder type, a bit less reliable data, at least for now, right? Because in the future, everything improves and things are getting better. But so to answer your question, I think how successful this predictability could become really depends a lot more on that, on those fields and those type of studies and those type of data in my mind. The practical aspect of integration of creating forecasting models for this purpose, I think we're probably already there. It is possible to do these sorts of integrations and combine. I would just be, as I say, like skeptical. They would be interested in modeling, how to call them, assays, but I would be more skeptical about the conclusions, to be honest, at least right now.
Okay, thank you very much. And thank you for the talk. It was really, really interesting.
Thank you.
Yeah.
Thank you.
If there are any other questions, of course, feel free to ask.
Kostas, I know your nodes and links, you're attempting risk analysis. But for me, looking at the schema, I feel strategic risks are harder to capture and especially in lag data like this. We've been debating AI in a number of forums in India, and the company I used to work with, they have huge, essentially, they have invested a lot of money into making sure a lot of detail is captured. You mentioned equipment data, resource data, and so on. My big concern is what I have seen is that when you do risk analysis during implementation, there isn't so much to benefit from. Most of the benefits come during the proposals. I'm more talking from a contractor point of view, and that's where my experience also is. So the contractor view and the proposal perspective is important for, I think nobody is trying to capture or bring in AI for proposal management. And I think maybe as nodes and links gets further, you would be able to capture risks across a portfolio of projects, construction projects, not just within the project. Does that sound? I mean, my comment, does it sound okay to you? Or?
Definitely, it definitely does. It's very interesting actually that you mentioned this, because it's also good for us data scientists to try and get this kind of intuition that we're missing, that people with actual experience in projects do have, and to see how what are the more important facets of a project, and in terms of being able to essentially leverage historic data or data aggregated across a number of projects is something for the future maybe, but at the same time I think with more interesting and with a larger potential in the end, because what you're talking about essentially means maybe even tackling larger issues that the whole industry is facing, but they don't really know about, or that the whole company might be facing, but they don't know about. So it's interesting. It's certainly where things are also going for nodes and links. It has been in our minds for the future, and as we keep gathering, collecting more and more data to, as you mentioned, not just work on a single schedule, but try to extract information from looking across many different projects and schedules, and make statistical estimates as well, and perhaps be able to identify more systemic kind of issues rather than issues concerning a single piece of work, a single project. So yeah, definitely, it's very interesting to hear this perspective.
Thank you, Kostas.
Thank you, Chakrada. Am I pronouncing your name correctly?
Perfect.
Thank you, Chakrada.
Okay.
I just want to reiterate something that Christos wrote in the chat, which is that Nodes and Links is hiring. I assume Christos is either the founder or a hiring manager. So
This
if
is
anyone
one of the two founders, yeah.
If anyone is interested,
and CTO of the company as well.
I guess it's worth knowing that there are job postings available. Any other questions?
Yeah, just another small one. So it's a small one. I mean, so if I understand correctly, so this let's say these methodologies can be applied also if we want to connect on a European level institutes, correct? Like if you have onboarding of services on a larger platform, like the European Open Science Cloud, could this be applicable between the various partners of a project and an overall arching structure that encompasses all of these people trying to populate it with services, let's say?
I think certain elements would be obviously the way that the platform has been growing and the data science behind it. The way it's developing, it's to kind of customize on project schedule data. But I think the mathematics, the concepts, it can be equally applicable. It's just a matter of using a different data set, let's say a different template or something. But I think the maths, a lot of the informational part can be applied to coordinate different types of projects, different people, and use it for other purposes, essentially. So I think the math, or a lot of the math discussed in here, can certainly have applications to to other similar but not exactly the same, not exactly the same kind of concepts.
Okay, perfect. Thank you very much.
You're welcome.
Kostas, I was also wondering, since a lot of these graph, a lot of the math behind what you were saying has to do with networks, and they're not necessarily related with, say, machine learning. But I was also thinking that there are these graph neural networks which are very popular nowadays, and whether there is any application, whether they are relevant in nodes and links, essentially.
Definitely, I'm pretty sure they're very relevant. So I think the general approach followed here can be termed, complex systems or complexity science, something like that, or network science. But that is one stream, like complexity, networks, dynamics, these sort of fields. It's definitely the approach that I've been mainly discussing today. But there are other approaches that can have, I think, a lot of use, and we're also thinking about it, for the future, for what we're going to do in the future. Machine learning definitely encapsulates classes of techniques that can be very useful. Also, the type of data that we have. We're talking about, as I mentioned, 20 or more tables, and each of them different number of columns, not all numerical. Quite a lot of them are, text, essentially names and those sort of stuff. So it is amenable to, completely different types of analysis, like more machine learning oriented. And I'm pretty sure in the future we are going to incorporate components from those approaches to the product.
Sweet. Are there any other questions? I'm happy to wait until everyone's questions have been answered. Another small one and really quick for me that I was thinking was whether, of course, these projects you described, Kostas, they're quite big projects, and for good reasons. Of course, it only makes sense to do this analysis in bigger projects. But is there some sort of metric limit or way to know? I mean, this is a business question essentially. Is there a way to know whether there's a project has a size that can benefit from nodes and links, and if it's below the size, essentially these techniques are not very applicable?
Very good question. A very good question. It's interesting to think about for me as well. In principle, you can apply this stuff, to the project of any size. But obviously, if it is too small, maybe a lot of these concepts do not really apply, and you don't not really care about them. I'm not sure if there is a way to somehow figure out the limit, but I think I can give you some actual, an idea of actual numbers. So many of the projects that we receive can be from 500 to 100,000 nodes, essentially. And it could be anything in between, depending on size. More commonly, though, I guess if they're up to 10,000 nodes, they're more common. If they're above 10,000, they're probably, really large. They would really benefit. Below, if we're talking hundreds, like I think even for a 500 node project or even a 200 node, probably some of these concepts apply well, and there can be benefit just out of some data sets that I've seen. If we're talking about, I've never seen any project, below like 200 nodes. So if we're talking below that, I'm not sure. I think some research would need to happen to see. And also, it's not just research. I think it's also the field expert perspective as well. Like because with any model, it's impossible to have, you know, a super accurate model that acts as a perfect representation. And for project data that I mentioned, it would be something like a huge multi-layer network where many network science algorithms and AI, like machine learning algorithms, are running on that, and you do, you know, huge simulations. But then one is asking whether that has any use. Whereas with smaller models that are definitely not, you know, representative fully of reality, but where you can extract some useful insight for practical questions, you know, that is generally more useful. So I think to answer the question, we would have to, it would have to happen some extra research from data scientists plus collaborators from project planning, like planners, to see what questions are they interested in if they have to deal with a 50 node network, like a project of 50 activities.
Kostas,
And then, you know, yeah.
If you allow me, can I paint a sexy picture?
Definitely, because I was finishing here anyway. I wasn't going to add anything.
So next question towards the smaller end of the spectrum. So when I look at AI, which is doing confidence modeling, when you have smaller projects and when you bring in the confidence level of the team, that's when AI really becomes beneficial. And also the context matters quite a bit. When you look at especially Indian projects or projects in Africa, for example, the dynamics are different. And so there's a challenge there. And I feel that even 20 activity projects, even if it's only for 15 days, there is a lot to be done. For example, there are some really super fast projects when you build solar farms. And as you can imagine, the Chinese teams have built about 10 gigawatt farms in 2.5 months.
Yeah.
The network structure for that is very, very simple. But I don't think anybody else is anywhere else in the world is capable of capturing that speed.
Yeah.
Yeah. So that's where I mean that's the sexy part of where nodes and links in the future can get to. But, so I thought I'll add that.
It is super interesting to get your perspective on this, Chakradhar. It's really interesting to hear. And yeah, going back to the question of size, it's a very, I think it's a very interesting question to look at.
Sure. I hope that helps, Nick.
Is there anything else? Any other questions?
Nick, your response would have been helpful, whether hearing the sexy versions of what nodes and links in the future could do. For small projects, does that help help you in your thinking?
What do you mean? So I don't work for nodes and links.
No, I know, but the question, our comments came from your question. So, and here I think the conversation has moved to what AI or what data science can do for projects in the future. So pushing those boundaries is what your question is helping us do.
I was mainly asking, to be honest, I didn't have a particular application in mind. I mean, I work in NLP in particular, and there are some graph neural networks that I'm aware of. So I was wondering whether they apply in this case. And similarly, for the small project, I was thinking only that, you know, like a lot of projects in here in Cyprus, infrastructure-wise, are quite small. For example, is this something that can apply there? But just out of curiosity.
Okay, lovely. Thank you.
If there are any other questions, feel free to ask. Otherwise, we're going to call it a day. We're going to release this in our YouTube playlist. So, so you can have it and watch it afterwards. We plan to do another meetup in a month, and we actually also plan to have it as a physical event. So if you're in Cyprus, in Nicosia in particular, we're probably going to do it live, but we're also going to have a Zoom link as we have here for people that are not either in Nicosia or in Cyprus. So we look forward to seeing you in the next one. Thank you very much, Kostas.
Cool. Well, thank you for the invitation. It was very nice, and the questions, the conversation was really nice as well. Nice to meet everybody, and see you in the next one.
Perfect. Bye-bye.
Bye-bye.
Bye.